So I thought I would start my talk with a California story. These pictures originated from the former governor of California, Leland Stanford, in 1872. Up until that time, there were controversies concerning whether in animal locomotion, such as this horse, there was really ever a point where all four legs were off the ground. And there are artists' visions, paintings of horses running, in which they have the horses with their legs out front and their legs behind like a diver going off a diving board. They're completely wrong. And this was a controversy for a long time. And Leland Stanford took a position that he felt there were instances when all four legs were off the ground, but how do you prove it? The motion happened too quickly to observe with your naked eye. So he hired a guy named Edward Muybridge, who was an Englishman, originally Edward Muggeridge, who changed his name to what he thought was the Anglo-Saxon way of saying it, but that's another story. And he became famous in California for his photographs of Yosemite. So Leland Stanford called him and said, I would like you to take pictures of animals moving so that I could prove whether all four legs on the horse are off the ground simultaneously. And the result were a collection of photos taken with millisecond or thousandth of a second resolution that definitively showed as you can see, that there are instances when all four legs are off the ground. And they're not like in the artist's photos where the horse looks like he's diving off a board, but they're when the legs are under him. So this required photographs taken on a thousandth of a second time scale so that you could see what was happening. And the topic of my talk, and you may want to Google Muybridge because he's a very interesting character, having been acquitted of cold-blooded murder and so on. So my talk is about how physicists in my field are trying to observe matter on its natural timescale. Just like Muybridge was observing horse, animal, he extended his studies to other animals. Animal motion. Atomic physicists are trying to image the way electrons in matter move. And for those of you who are interested, there's a very nice web page called Atto-World that discusses many of the aspects of this field. So my talk will be to go through some terminology and timescales and motivation for my field, and then bring you up to date to how this is done by beginning with explaining what is a laser and how you get lasers short and intense, and then showing what has been done and what is likely to be done in the near future here. So, motivation. Well, this is the densest slide I'm going to show. But it's early, so you probably won't fall asleep. What is attosecond physics? I would say it's the use of ultra-short pulses of laser light. Now, every word in a physicist's language is important. So, ultra-short pulse laser light. Every word has meaning, and I will try in the course of this talk to explain these words. To understand, control, and image ultrafast atomic and molecular processes, because Why is it important? Well, it will allow one to study chemical reactions in real time as they occur. You know, right now, what do chemists do? They mix some things together, and then they figure out what they've got. They have no idea how to go from mixing the things together to what you end up with. Because things happen on a time scale that's so fast that it can't be observed. The idea is if we could observe atomic, molecular, electronic motions as they occur, we will, one, gain understanding of these fundamental processes like photosynthesis. People really don't understand photosynthesis. They would love to know how to make it more efficient to capture sunlight. But you don't have a way of seeing in time how the changes occur. And if you don't see it that way, you can't manipulate things to maybe improve on the way things are happening. Okay, so what are the key problems? Well, first, on this scale, electronic and molecular motions, things happen very fast. And so if you're going to image them, the pulses must be ultra short. That is shorter than the time scale of atomic and molecular processes. The key problem is that the most common laser pulses are much longer than these processes. So attosecond physics has had to devise ways of making laser pulses shorter than the time scale on which these chemical processes occur. And the way they do it, as I will go through and explain, is that they employ the ultra-short bursts of radiation emitted by laser-driven electrons. So, and as I said, when a physicist talks, it's like legalese. Every word has a meaning. So laser-driven electrons, that's what you have to focus on and remember. The other thing, if you're going to control these processes, once you understand them, your laser pulses must be strong enough to actually make a difference, because you know, atoms and molecules, they have forces that hold them together. Electrons are found in atoms. These laser pulses have to have strengths comparable to the Coulomb forces between nuclei and electrons, to the Coulomb or van der Waals forces between two molecules, and so on. And that requires higher electric fields. And the problem with making such intense fields is that when you do that, they destroy all your optics. And I can tell you, when we set up new professors, 30 years ago it might cost $10,000 to set up a new assistant professor in atomic physics. Nowadays we're talking 800,000 to $1 million. That's what the University of Nebraska pays to set up a new assistant professor in AMO physics. It's much higher than the rate of inflation. So when the politicians say that universities are raising costs higher than the cost of inflation, they're ignoring the fact that research universities costs to do cutting-edge research is going up much faster than the cost of living for milk and bread and so on. Because to stay at the frontier of knowledge is very expensive to keep at that frontier. How do you avoid this? Well, that's something that may eventually win the Nobel Prize, perhaps. It's called chirp pulse amplification. It's very simple, actually, once you know it, of course. Okay, so let's talk about terminology, because this talk is about Atto-Physics. This shows you all the Latin roots that are associated with powers of 10. And this column you can read, these are big numbers, but my talk is about the ultra short, so I'm going to focus on these small numbers. The time scale needed for the Muybridge photographs of the horse motion had to be on the millisecond level, that is 1,000th of a second, which is 10 to the minus 3. And then you go up. There's a new word for every 1,000. So a millionth of a second is a microsecond, and a billionth of a second is a nanosecond. Nano should have reached into the popular culture. And when you get even faster than nano, 1,000 times shorter, picoseconds, and femtoseconds, and then attoseconds. An attosecond is a billionth of 1 billionth of a second.
Nano.
No? Yes, it's nano. It's nano squared. So why is that necessary? Well, there's a cover of New Scientist, a British magazine. Welcome to Atto World. Ponder this subtitle. Where a second lasts the age of the universe. What the heck does that mean? A second lasting the age of the universe. Well, time is relative. I've given a whole lecture on time. But for us, humans, our time, since we live on average 80 years plus or minus a decade or two, the time it takes the Earth to go around the Sun, 1 year, is reasonable because that's smaller than our lifetime. We want to subdivide a year. We use the revolution of the Earth on its axis, which is a day. And so we measure time in years, days, months, the time the moon goes around the Earth. In a hydrogen atom is the simplest atom. It's an electron orbiting a proton. And those who know quantum physics don't quibble. This is the Bohr model. Electron going around the proton orbits that proton in 152 attoseconds. So if you are to study electronic motion, you need some way of interacting with that atom that's shorter than 152 attoseconds in order to stop time. And I know you can't read the subtitle. This is from a Reviews of Modern Physics, a review of attosecond physics. But I just want to focus on the timescales here. Here's an electron going around a nucleus. The motions, it says, of electrons take place on attosecond timescale, which is 10 to the minus 18, as we saw in that table. Now, your heartbeat is roughly beating once per second, give or take a few percent. So, 1 attosecond is 1 billionth of a heartbeat. What is the age of the universe? Well, to the best knowledge we know, according to Big Bang cosmology, the universe is on the order of about 12 billion years, give or take a couple billion. And if you convert that to seconds, that's roughly 10 to the 18th seconds. So a heartbeat is to the age of the universe the same way an attosecond is to 1 second. So this is the origin of that subtitle, where 1 cycle lasts the age of the, 1 attosecond is the age of the universe, because the ratio is the same. 1 attosecond is to a heartbeat, the same as a heartbeat is to the age of the universe measured in seconds. It's a billion seconds. So that gives you an inkling of the magnitudes we're talking about. The other thing you should consider, and let's see, is that there are uncertainty principles in physics that say that uncertainties in energy times uncertainties in time are of the order of Planck's constant. This is an uncertainty relation. And generally, in physics, we know that the energies of motion of quantum objects is related to the periods of their motion. So if you have atoms moving on molecular timescales, in time, these are measured in picoseconds or trillionths of a second. And the energies involved range from 1,000, a milli-electron volt. An electron volt is if you took a single electron and accelerated it through 1 volt potential, its energy after acceleration would equal 1 electron volt. And atomic motions are measured on thousandths of an electron volt up to an electron volt. And the time scales are on picoseconds. When you get to electron motion in atoms and molecules, the time scales go from femto to attoseconds, and the time scales go from electron volts to thousandths of electron volts, or KeV, kiloelectron volts. When you get to nuclear motions, the time scales are measured in zeptoseconds, which is 1,000th of an attosecond, and the energies are measured in millionths of an electron volt. And remember that, because at the end I will mention something about zeptoseconds. Okay, so all of attosecond physics originates from lasers. And so it's appropriate to tell you what is a laser. I mean, I can tell you the meaning. It's the acronym for light amplification by stimulated emission radiation. But what does that mean? Well, the first thing you must know about lasers is that it's coherent light. And sunlight has many colors, and they're all chaotically streaming outward from the sun. Many of them hit the earth, but they're all out of phase. The radiation from different parts of the sun are incoherent. The time at which they radiate is completely uncorrelated with each other. If you have an LED, light-emitting diode, which now is becoming an efficient means for lighting, there you have a single color, but all of the atoms in the device are emitting independently of one another. So you have an incoherent emission here, incoherent emission here. When you have lasers, if you could get your sources of radiation to emit all at the same time, all in tune or coherently with one another, then you can get a much more intense bit of light. And I've written that here. That if you have, because the intensity of laser light, what's oscillating here is the electric field of the light wave. The intensity is proportional to the absolute square of that energy. If you have n emitters and they emit incoherently, well, you have n times the intensity of each one of them. But if they're coherent, then your electric field adds up. If you have n emitters, you have n sources of this electric field, all emitted in tune with each other. Then the intensity goes like the square, which gives you an n squared dependence rather than n dependence. So if you have many emitters, the intensity goes up like the square of the number of emitters for coherent light, as opposed to incoherent light, which goes up linearly with the number of emitters. Okay, what difference? If you have 10 emitters, that means incoherent light will be 10 times the intensity of 1. Coherent light will be 100 times. Okay, factor of 10. If you have a laser crystal, a centimeter on the side, atoms are separated by an angstrom, so there may be 10 to the 8th atoms on a side. You have a crystal that's a centimeter cubed, that's 10 to the 8th cubed. You have 10 to the 24th atoms. Maybe 1% of those atoms are radiating coherently, so you have 10 to the 22 radiating emitters, and you square that to get the intensity. So coherent light is dramatically more intense than incoherent light, and is more controllable. And how do you get such atoms to radiate? Now, to explain how lasers work, you have to go to a quantum picture. If you have an atom, let's just consider a single atom. As I told you, you could have 10 to the 22 atoms in a typical laser, but let's just take one atom. If in some way you can excite an electron from its initial state to an excited state, and a photon having a particle of light having exactly the energy difference of these two levels comes by, it can stimulate this electron to fall down and emit a similar identical photon of its own, so that now you have two. This light is composed of photons, these particles of light. They have energies, Planck's constant times their frequency, which is related to their wavelength in this way, and the frequency times the wavelength is the speed of light. Why don't we see photons? Well, I did a rough calculation of sunlight, and I came up with the fact that the sun emits on Earth 10 to the 22 photons per centimeter squared. 10 to the 22 is 10,000 billion photons on each square centimeter. So even though light originates from a quantum object, atoms, ions, there are so many of these photons that we regard it as a classical field, an electric field. But on the other hand, I used to be an associate editor of Reviews of Modern Physics, and one of the articles that I solicited and then edited gave me great pleasure. It was a biophysics group at Berkeley in which they described an experiment in which the human eye detected a single photon. What they did was they took volunteer subjects and put them in a room that was absolutely sealed, no light. They had to stay in that room for 3 hours. And then they had a gas of excited atoms where the atoms radiated so seldom, it was such a rare transition, that in all probability no more than one photon was emitted at any given time. And after 3 hours, these subjects were able to detect that emission. So your eye was biologically designed to detect even single photons. But in normal life, there are so many photons that we think of light as just a waving electric field, which is the way I will describe it. Okay, so I've described how an atom emits light. If you have many, many atoms, you can get a very intense, coherent source. And because there are so many emitted photons, we can regard the laser as producing an electric field that just oscillates up and down like this solid line here. Now, how do we get attosecond pulses, which is short pulses, to illustrate electronic or molecular motion what happens, and the next several slides are going to come back and explain in more detail, so this isn't the only slide explaining this. But when the electric field becomes strongest, this dotted line shows that an electron can be stripped from an atom, ionized, and it accelerates away, and then the laser field changes sign. It goes from positive to negative, so the electron, instead of going away, now comes back, and when it returns to the atom from which it was ionized, it can emit a pulse of light. And this pulse of light is generally of attosecond duration. And so by using intense laser light, you can get these attosecond pulses. Now this is a pulse train of attosecond pulses. If you instead of using a long laser field, you make a short laser field, then only this highest peak generates a significant number of electrons ionized, and they produce a single attosecond pulse. So it's possible, although this is more technologically demanding, that you can produce a single attosecond pulse, but it's more common to produce attosecond pulse trains. What do they look like? This is a spectrum of that pulse of light, that attosecond burst, analyzed in terms of wavelength, decreasing lambda, which means that the frequency is increasing this way. This is a trace, and this is the actual experimental data. Unfortunately, the data is plotted in increasing wavelength, whereas this is decreasing wavelength. So I would have to flip this over to match that. But the key point is that each of these bursts is a harmonic that has, the nth harmonic has an energy of n times the photons in the driving laser field. So you can see there are many harmonics. And so you can get, in this short attosecond burst of radiation, you can get pulses that can go to quite high energies depending on how many laser photons are in them. And now this is called high order harmonic generation. So this reviews in one place the past two slides. I have a driving laser field. I send in a gas of atoms. This laser field ionizes electrons from each atom. They return and create bursts of light that are attosecond pulses. A key understanding of this process was something called the three-step model, in which you have an atom, you have a driving laser field, you ionize an electron. And of course, on a quantum level, electrons are wave packets, we call them. They're distributed in space. And this initially moves away from the atom, accelerated away, but then the laser field goes from positive to negative. That electron wave packet is attracted back to the atom, and it recombines, and when it recombines, it gives up the energy of acceleration it's obtained by moving in this laser electric field in a burst of radiation, which contains all these harmonics.
Is this similar to stimulated Raman scattering, a nonlinear process?
Probably, yes. But this is in a different energy range. And now let me show you a movie of this to bring it home. So here you have an electron in an atomic potential. The laser field is on. It tips the potential that an electron has so that the electron gets ionized. But then the laser field changes sign, drags the electron back, and when it gets here, it emits this burst of light, and then the process happens again. The electron gets ionized. And this isn't the only thing that can happen. If you have many electrons in the atom, one electron can be ionized. Then the laser electric field changes sign, forces the electron to go back, and it could give up its energy. Instead of a burst of radiation, it could knock another electron out. So this is called lasers double ionization.
Tony, I'll point out that the maker of that animation is in the audience.
Yes. I'm very grateful to Francois Moget from Sherbrooke, Canada.
Do you have to filter out the original laser pulses, even though they're very different frequency?
Say that again?
Do you have to filter out the original laser pulses? They get through the gas jet?
Well, I mean, this is in a different frequency range than the bursts.
So it doesn't really matter.
Right. They're in different frequency.
Thank you.
Because the harmonics, the burst is harmonics of that frequency.
That's all you're interested in.
So one can think of this process that has enabled one to produce these attosecond pulses as a harmonic orchestra. So this is an analogy. You have a conductor, which is the driving laser field. You have a trillion of musicians. That's probably understated. For that reason, one shows musicians all over the planet. And they are all playing harmonics of that driving laser frequency. And a burst of these harmonics occurs every half cycle of the driving laser field. And so this is okay, so I've explained how one gets short bursts of radiation in order to study electronic and atomic motion. Now the question is, how does one get laser light intense? And I will do this quickly. I mean, I remember going to meetings in the 70s in which the laser people were off in a corner talking to themselves. There were so few of them. Because laser light...
Coherent or incoherent conversation?
Probably coherent. But the reason there were so few of them is that data was so hard to get. And lasers were so weak in terms of their intensity that the only way they could get measurable data was to tune their laser to an atomic resonance. Then when you have a resonance, then they could see something. And so many of the optical physicists that day thought of atoms as what we call two-level systems, a ground state and excited state, and that's all that mattered to them. But that changed in the 80s with, that began changing in the 60s. Q-switching was taking a laser from continuous operation to pulsed operation, but the pulses were pretty long. Then mode blocking got the pulses to be very, very short. But the big break, but then you had this plateau where people couldn't, by focusing their lasers into a tighter and tighter spot, the way you take a magnifying glass, hold it in the sunlight, and try to light a fire. You know, that's how you get the sunlight to focus its energy in a particular point. You raise the intensity at that point. But what would you think if your magnifying glass were melted by the sun? I mean, that's what happened when people tried to get lasers too intense. And that was solved with chirp pulse amplification, in which Gerard Moreau and Donna Strickland decided to take a laser pulse here, you want to amplify it, make it bigger. What they decided to do is send it through a grating which separates the colors. That's what gratings do. And they separated the colors in time. So now the yellows and the reds enter your amplifier at a different time from the blues and the violets. And so now the amplifier doesn't get destroyed. And you amplify every color. And now you do the reverse process of putting the colors together back into this enormous pulse. And so this chirp pulse amplification allowed these short pulses to become laser light to become more intense. Okay, so what?
Doesn't the last grating blow up then?
No, because you gratings can be made. Well, okay. I don't know. I'm a theorist. They must have some material that can survive. But these amplifiers don't have that material.
It's coherent light. I mean, isn't out of the laser? Well, how do you get colors out of it? Yeah. The laser is coherent. There aren't a lot of colors.
Well, it's a pulse. Don't forget. So
there is a band.
There's a bandwidth.
There is a little bandwidth in the laser light, even though it's a
one frequency.
But there's some
yes.
bandwidth to the monochromatic. So
Right.
there's separated.
That's right.
And certainly not the light in the rainbow then.
No. That's an exaggeration.
Right. Yeah,
but
exactly. Yeah.
it's for illustrative purposes. And
Yeah.
okay, so these, I'm going to show you a number of things that people have in mind doing and have done, and then look more toward the future. This is a schematic diagram for what one would like to do with short pulses of attosecond pulses. These diagrams describe states of a molecule. And the idea would be that if you have an electron in this lowest state, you pump it up with an attosecond pulse to some intermediate state, and then you could get a second pulse and pump it up even higher, or you could let this evolve in this potential, and then with the second pulse move it down to an excited state in the ground potential. And in this way, use lasers, pump and control pulses to manipulate how electronic motion proceeds in a molecular system. This is a more detailed simulation for a huge biomolecules called tyrosine terminated tetrapeptide. What's happened here is an attosecond pulse has ionized an electron, creating an excited state at this end of this molecule. And 250 attoseconds later, you see that this excitation has moved. 500 attoseconds later is moved even further, and now 750 attoseconds later, or 0.75 femtoseconds, the excitation has moved to the other end of the molecule. So these excitations in a biomolecule traverse the molecule on an attosecond timescale. So how do you image this? Well, image what the theorists who are simulating this have done is that they just sent in another attosecond pulse at these different times and some later times as well, and showed that the spectrum, the energy spectrum of the electrons ionized from these different states are very different as time goes on. So one is seeing here from these different spectra changes in the molecular structure as a function of time. And so this is the beginning of really seeing how atomic and molecular processes proceed. Okay, that is all theorists simulating what they would like to do. Here are some real things that have been done by experimentalists. Here's a single crystal of tungsten. Tungsten has a conduction band, it's a metal. It also has deeply bound electrons in localized atomic states. If you have an attosecond pulse come in, it can ionize electrons in the conduction band. It could ionize electrons deeply bound in each atom. What they found when they measured the electrons that come out is that electrons in the localized states appear in the detector 100 attoseconds after electrons from the conduction band. This is the first time the time scale of ionization has been seen. And this is a real experiment. This is one of the achievements of attosecond physics. Another that's still controversial because theorists can't predict it is to take neon. Neon is an atom with 10 electrons, and one has a shell model of atoms. There's a 1s shell, 2s shell, 2p shell. All you have to know is the 2s and 2p are the outer two shells. They have different binding energies. And what they found was that these are the electrons from the 2s shell, and these are the electrons from the 2p shell. The 2p are outer, they have lower binding energy, so they have higher energy. But these electrons appear 20 attoseconds after the inner shell electrons. So here the 2s electrons are appearing 20 attoseconds before the outermost electrons are appearing. And theory has still not been able to explain this. The best theorists have been able to do is come up with the 10 attosecond difference. Okay, so to summarize, where does ultrafast science stand? Let's go through again this talk. If you use shutters on cameras, you can measure animal mechanics on a millisecond time scale, thousandth of a second. Another fellow Nebraskan who became famous was Edgerton. He became a professor at MIT, and he studied through strobe light photography events that happen on a millionth of a second, microsecond. This is a drop of milk falling in a pool of milk. This is a picture of the splash it makes. If you have electronics, they work on nano time scales, billionths of a second. That's how fast you can switch electrons. Pulsed lasers, as we talked about, operate on pico and femtosecond time scales. And then you have electronic motion that operates on attosecond time scales. But what I want to, other than just giving you names of things, the physics is very different. When you have microwave electronics, what you're doing is using voltages and currents to control electron motion. When you have ultrafast optics, you're using the intensity of a pulse, the envelope, to control electronic motion. Now, in attosecond physics, when you have few cycles, the idea is to let, if you have very few cycles, let the electric field inside an envelope control electron motion. And this is called light field electronics. And this is the new thing that's just occurred in the last few years and that will be used in the future. The Italian group in Milan were the first to obtain few cycle attosecond pulses. They obtained a single cycle pulse that was 150 attoseconds wide, and this picture enables them to determine this, and I have not explained that picture, I just put it up because it looks pretty. But look what they say about their data. The availability of single cycle isolated attosecond pulses opens the way to a new regime in ultrafast physics, in which the strong field electrodynamics in atoms and molecules is driven by the electric field of the attosecond pulses rather than by their intensity profile. So it's using the field rather than the pulse envelope. And so, where do we stand now? Well, as I've tried to explain, high-order harmonic generation has allowed the production of isolated pulses of attosecond duration. Experimentalists have determined the timescales of electronic motion in a number of atomic, molecular, and condensed matter processes. Controlling such processes is just beginning. I forgot to include here that lasers have been used to turn what's the opposite of conductor? Insulator. They've been used into a conductor on a femtosecond time scale. So that's a means of control. I should have added that. But what about the future? Well, I mean, just think big. You know, if you don't think big, you're not going to achieve things big. High-order harmonic generation may lead to coherent lasers in the water window. Right now, the only lasers we have are in the visible region. If we could extend them into the water window, that is, photons of energies between 280 and 530 eV, or wavelengths in these range, then what is the water window? If you shine light on a living object, most living objects are made of 90% water. And if you use visible light, you don't see anything because the water absorbs the light. But in the water window, what is water? Water is H2O. It's hydrogen and oxygen. In this energy region, oxygen is transparent to radiation. So the water in a living system that makes up 90% is transparent to laser light in this energy region. What isn't transparent is the carbon and the nitrogen that make up all your tissues, all your organs. So the vision would be, you could walk into your doctor's office, you could turn on a laser in this energy range and make a hologram and watch your heart beating and walk around and see all aspects. Of course, that's pretty far-fetched, but taking living matter on a slide would be realistic and obviously the first thing that could be done. What about nuclear turning? David Gross, the former head of this institute, was very excited when he heard that AMO physicists had obtained structures that were zeptoseconds long, that is, shorter than 1 attosecond. If one could develop zeptosecond pulses, this is 1,000 times shorter than an attosecond pulse, one could begin to envisage nuclear timescales, nuclear motions. And lastly, what I've talked about intense light was to make the driving laser field intense enough to get the attosecond pulses that we need. But these attosecond pulses are still weak. Experimentalists need to make them more intense. And when they do, and it's expected that they will in the next few years, one will be able to do attosecond pump, attosecond probe experiments. That is, one pulse will initiate a process, and then the other, by varying the time delay, will be able to take a snapshot of the process as it occurs. This is the dream of attosecond physics. The other thing about intense attosecond pulses that have few cycles is that since the electric field determines the motion, you can get asymmetric motions. You can kick an electron more in one direction than the other. And so these intense attosecond pulses can control electron angular distributions, or in simple language, which way an electron moves, whether it goes to the right or the left. And that's an example of the control one will have. And so, I thank you.
Question here.
Yes?
So
So you talked about with this attosecond pulse generation using IR femtosecond lasers in getting X-rays out. You know, most chemical reactions and most electronics are occurring not on hundreds of eV scales, but you know, a few eV or tens of eV. So I wanted to ask about what are the prospects for using much you know, lower frequency pump, I don't know if that's radio waves or what, to get you know, things that are IR, visible, UV, output pulses.
The lowest energy attosecond pulses have been around 25, around 35 electron volts, which is quite high compared to the energy scales you're talking about. But those energies in molecules, I think femtosecond pulses would be sufficient to study them. Many of the heavy particle motion, Ahmed Zewail has got the Nobel Prize for femtosecond chemistry, in which he used femtosecond laser pulses to measure heavy particle motion. The idea here would be, yes, to use attosecond to measure electronic motion, but I think the experiments that have been done have simply ionized an electron and looked at what happens to the ion, and what happens to the vacancy that has been left behind. And as I showed you, the vacancy can migrate from one part of the molecule to the other. But you're right that attosecond pulses are too energetic for the typical energy scale of molecules. Yes?
And I'm curious, this water window you describe up there for looking at a person, it seems to me those are rather energetic photons, and that would be damaging to a lot of human tissue in those energy windows. Pure water is one thing, but there's a lot of other stuff
Well,
to worry about.
this is actually soft X-ray.
Soft
When you go
X-ray.
when you go into a doctor's office, they're using harder X-rays.
You've already been hit with something worse.
Yeah.
This is the soft X-ray region, and
Well, but still, you don't shine a lot of soft X-rays in your face and all over. It's,
yes, I mean, you're asking about the health effects of being exposed to such things, and I think one could have a weak enough pulse that it's no more damaging than an X-ray, dental X-ray.
I'm confused about one little detail when you show.
Only one. That's good. That's good.
What I want to ask about. When you show the high harmonics generation, it looks like one wave, and every time you go to zero, you generate an attosecond pulse.
Yes.
But we have the uncertainty principle. It's not one frequency. Femtosecond pulse is, I don't know, 1,000 wave numbers. So there are many different frequencies.
Yes, yes. I mean, the attosecond pulse is not a single frequency, as I explained when you
Right, but here is the femtosecond pulse that you start, that you generate the attosecond pulse.
If you have a long femtosecond, if you have a long pulse, it becomes monochromatic,
Right.
very low. But if you have a short one, yes, you're right. It has a long one. But one is not so concerned about that. One uses, as I showed, these short pulses to produce single attosecond pulses. And they do have. So, what is your question? I agree that if you have a driving laser pulse that's short.
It looks like a neat pulse train of attosecond pulses correlated with a single frequency femtosecond
That's
pulse,
right.
but it's not a single frequency. It's a femtosecond. That was my question.
Well, the attosecond pulse train is generated by a monochromatic long laser pulse.
Oh, okay. I thought you said it was a femtosecond pulse. And
What's the
femtosecond
levels
pulse
on
cannot be
How big is
monochromatic.
N? Is that what harmonics? The N of 100? N of 10?
The harmonics could go
Yeah, but in terms of down
from 3 to 1,000. But
Right, for a femtosecond pulse, you probably have 100 wave numbers in that packet, and so then that presumably gets broadened by the harmonics,
But when you talk about femtosecond pulses, usually these things are 50 femtoseconds or 100 femtoseconds, so they're pretty long in terms of the number of cycles, because for the high sapphire laser, the period is about 2.7 femtoseconds. And so if you have a 100 femtosecond laser, you're talking about 25 cycles, and that's essentially monochromatic.
Please.
Yes?
How do you detect your attosecond pulses?
That's a good question.
Trust
That's a
me.
very good question. And my being a theorist makes me pause here.
Is it very different from femtosecond pulses, or is it a totally new technology, yet you need new, special detectors? I don't know what.
Usually,
What's the setup?
you detect what you've produced by having them ionize an electron,
Right.
and then doing something called attosecond streaking to make these traces. Generally you have a femtosecond, you have an attosecond pulse. It ionizes an electron. You have a driving laser field in the vicinity, and then the electron will be shifted in energy by that field, and they have these computer codes that have them take the data they obtain and create a pulse shape like this. These computer codes go through 5,000, 10,000 iterations. It's not a
Okay,
simple
you have
thing.
to collect a bunch of pulses and do
Right.
some kind of, so.
But
Derived.
they don't know exactly what they've got.
You don't get a picture. It's built up from data that you collected on the interactions.
When they're pushing the envelope all
Yeah.
the time.
You still need very, very fast detectors somehow, and I
Yes.
don't know what you use.
Well, there's no detector that will do that. It's response times.
Great. Well, let's thank Toy one more time.